And we're now streaming, so we're live from downtown LA. Yeah, that's what we're called.
Yeah, that's a strat, but you can't be saying that. This is the secret strat. Yeah, I just lost it.
And question that slide, preview, save.
What's this?
Okay, is everybody ready?
Is there no other data?
Excellent. You'll need your computers or a phone.
These are. Which sandwich is better? This one is just so.
No, really? No, wait.
No.
I got my phone. Okay, we're gonna do a strat. When we know the answer, we're gonna yell. This is all fire.
Wait, is this the pop quiz?
This is the pop quiz.
I just searched for my piece of data booklet in my whole binder. Look at my binder.
Nice. There's more. Pardon? You now have to.
Look at this.
That was more to get everybody off what they were doing.
Is
No,
that
that's not cheating.
This is a quiz. Formative quiz. Timmy? Timmy?
Wait, can I try that? You go?
Timmy! Take off the headphones.
Yeah.
Sit down. Get out your data booklet. You're getting ready here.
My data book is out.
Okay, piece of paper. Not drawing on the whiteboard.
I have my piece of paper. Wait,
Pardon?
are we joining this?
Join. Joining. Oh, why is it doing this?
Can we do it on our phones or laptops only?
That's my high school.
Mr. New?
I'm going to restart this.
Let's get that.
Mr. New? Can we do it on our phones?
Randomize, autoplay. I will play it. Don't autoplay. Okay, everybody join. We've only got Lisa.
That's actually good.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need 10 people up there. Yes?
Can I borrow the extension things that you said?
Extension things?
Like the extension cords for
Yeah, absolutely. Yeah. That's what they're there for. I'm just going to get attendance up and going while everybody's signing. 1, 2, 3. We only have 4. Come on. Chop, chop. Yep.
Do you have any more of the booklet, data booklet?
Grade 10? Yes. Sorry, my brain was like.
My baby.
They're like
my
a
baby
penis.
has a penguin and the goggles. So lucky I might
Here's
be a
one.
penguin.
No. Wood.
Oh, mine's so cool.
Wood.
Whoever's a penguin can't be the penguin. That's already weird.
Okay, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yes.
1, 2, 3, 4, 5, 6, 7, 8. We're missing 2 people.
Actually, I was going with second.
And I know who one of them is. Because you're just getting started. Who's the other person? 1, 2, 3, 4, 5, 6, 7, 8. Show me your screens. Who's not got it? You're there. You're there. You're there. Got it. Got it. Got it. Got it. Got it. 2. 2. Oh, and attendance. Where is everybody today? Say, Timmy's here, Ben's here, Jonathan's here, Ariel's here, Zoe's here, Lisa's here, Felix is gone, Zane's here, Matthew's here, William K's gone. Question? No? Okay. Alejandra's not here, Bertie's not here, Kieran's not here, William Brennan's here, Naomi's not here, Hugo's here, and Sahir's, yeah, how many we're missing? 1, 2, 3, 4, 5, 6, 7 people. Out of 17, at least we got more than half. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, I assume
I'm not-
you're almost there?
No fun question, Ted.
Just so you know, I've been teaching since 1999, no, 98 actually.
Who's Joe?
I only used Kahoot for the first time like yesterday.
Did you like it?
No.
Oh, well.
But on the other hand, the students, they're grade
Yes,
12,
yeah.
seemed really excited. So rather than giving you a quiz practice, I put all the questions on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. Start.
Can I write down the questions?
Yeah, you can do whatever you want.
Why are you supposed to have some paper?
Y'all already know what's going on. If Mr. Goofy drops, who do you play?
Bro, whoever's playing is just guessing. What's G?
Wait. Oh, the height count is. No, the height's not in the last. Screen.
Oh,
Go,
you only
guess.
need one answer. Oh,
Screen.
I don't have a calculator.
why did I think of that?
Well, for that particular, grab one. I will grab one for you. However, did you need a calculator for this one? No, why did you need one?
The rest are speeds.
The rest are speeds. It's the only one that says joules. Units are important.
Oh.
Potential energy and kinetic energy in joules.
Nice.
Julio.
I'll see if I can find you a calculator.
Lock it.
Yeah, good one. This one still works. This calculator's like 12 years old. Nice. Ooh, that was good.
What?
I think in this speed matters as well. Like you get more points the faster you are.
Yeah.
No, my God.
Those were that.
I saw you. You put it on the other side because you thought you could click it.
Julio?
Wait, don't you have to? I got it. Oh, I did.
Because roughly, what's gravity?
9.1.
9.81. So if you're doing things fast in your head, just make it 10. Boom. And as long as the numbers are really close together, you can get estimates. If you go into astronomy, professional astronomers when they're doing stuff, guess what? Pi equals 10.
What?
Because they're dealing with millions of kilometers and stars with thousands and, not thousands, billions of joules of energy and all. Pi is equal to 10? It's fine. They don't need real
Possible, like,
circles.
extra 600 years of travel.
This is actually in our very next set of notes. Nice. Everything eventually becomes heat. It's called the heat death of the universe. Ooh. Johnny?
It just like.
Oh, it's just like this.
Okay.
I do that a lot.
50 kilojoules, so it's 50,000 joules.
Or
That's
No one's still in
After the next unit, I'm gonna revisit SI units because that'd probably be useful.
completely
Wait, I don't get that.
I didn't know.
But for the one person who got that, well done.
Yeah, I did that.
Nice.
Bro, I misclicked. I misclicked.
Ooh, a little bit of movement, a little bit of movement.
I misclicked. Bro. Not my fault.
Ooh, nice. Oh, I should have waited.
No, I clicked the wrong ones. No.
And there's no way to undo it. I hate
I
that.
clicked the wrong one.
Wait, what?
I clicked the wrong one.
Wait a minute. Oh, gravity.
There we go.
The wrong one.
Oh,
Yeah, well, you're winning,
Beautiful.
buddy. Good job. Good job.
Oh, I clicked the wrong one. Oh no.
Wait, I clicked the right one.
oh, movement. Excellent, excellent, excellent movement
I
there.
clicked it. I clicked it.
Wait, that's yours.
Ooh, you go. If that is indeed your real name.
How are we supposed to figure this out? With the formula?
One of those.
Wait, so the kinetic energy is like half the mass?
Chelsea.
Is that what it means? Because if not, then I've been doing things wrong.
Kinetic energy.
Yeah, it's 1/2 times M. But for that one, you use MGH. Because you take the 30,000,
Well, yeah, no, I know
divide by
that.
10,
But I mean,
divide
it's
by
like in
10.
general.
Yeah. Yeah. So the kinetic energy is 1/2. So mass times V squared divided by 2.
Wait, why is
Or you can half the mass, whatever you want.
Oh, v squared divided. Oh, yeah.
Yeah. It doesn't matter what you have, as long as you do it. Ooh. Does speed make a difference in this one? Too much. A manifestation of guilt.
I should have clicked it. I should have clicked that.
Chelsea?
Those of you, you don't have to tell me if you don't want to, but those of you who picked blue, why? What did you do that was different? What did you forget to do?
I picked the other one because blue wasn't right.
What?
The blue just didn't look right, so I picked the other one.
I just got the vibe that 3 was right.
Well, you go MGH, so I'm guessing you that one forgot to multiply by G, because that would be maybe mass
I guess.
times height.
Wait, how did you figure that out? That also.
Energy of the potential energy equals equals mass times gravity times height.
Yeah.
So just multiply them all together, and all of the potential energy gets converted to kinetic. So they're the same thing just before it hits the ground.
So it's just P.
Yeah, it was potential energy asked as kinetic energy.
No,
Oh.
Yeah.
yes.
Ooh, nice to know here.
I knew that.
Nobody picked 0. That was the true distractor.
I was so close to picking.
We're just going
Yes.
They don't mind us from each other. Good, well done. Second to last one. I should make the last few worth double points.
Base?
What's T?
Total energy.
Biggest one. No shoot.
I think 1/2 mv squared of that is like 100, and then MGH comes out to 50. So when you add them together, I think that's where you got 150. I like the spread though. Last one.
Uncle Joseph.
I dropped it.
Why did most people pick? Oh, you forgot to multiply by gravity?
I clicked the wrong one.
Fair.
That was.
Oh, podium. Congratulations. Congratulations. Oh, you get a ring and everything. Well done. Well done. Excellent.
Gave you the 200 points. No, actually, the last one I did by myself, and that's why I got it wrong.
Okay, now put your phones and everything away.
I got 10.
Look, William. Good job. I think you're such fast. Really, thank you.
Phones away. Laptops away.
How did we get the data?
Oh, I did look
Come on.
What's your wallpaper?
Sorry?
What's your wallpaper?
Recognize the character?
Oh, that is from Portal.
Portal.
Oh,
Oh, yeah.
What's the robot?
I don't know. It's upside down.
Well, you know, she moves. I do love that moment in spoilers for Portal, so cover your ears if you don't want to hear it. I do love that moment where she realizes that she was programmed from a human woman all along, and she has feelings, and you think that's going to be the great reveal like they have, and she'll be good, and then she goes, files deleted, and then just turns back into being evil. It was lovely. Perfect. I did say spoilers. Hold it, where is... That's that one. Okay, and then I want... Yo, what up?
How many wallpapers do you have?
I have thousands, and they change like every 7 minutes or 10 minutes or something. This one's kind of disturbing because clearly robot, but also clearly trying to escape. So sentient robot, which makes it a little disturbing. Oh, and look, it moves. Potential energy, kinetic energy. Potential energy, kinetic energy. It's also doing work. Okay. So, first one you already know. What is the law of conservation of energy?
Energy cannot be created nor destroyed.
So it can only be transformed. Potential energy can become kinetic, kinetic can become thermal, both can become thermal. You can move energy around, but you can't create it, you can't get rid of it. Although, secretly, the law of conservation of mass is equal to the law of conservation of energy. If I wrote that in an extremely messy way, I don't even know if you can read energy off of that. But Einstein's great, well, one of his many contributions, we learned the law of conservation of mass and law of conservation of energy are actually the same thing. Nuclear power is when some of the mass is literally being converted into energy. So these don't work once you get into nuclear. However, it's still held because we've learned that mass and energy are actually different forms of the same thing. And when you get down into string theory, we learn that mass is just a property, it's not from stuff, and that everything just might be charges being held like strings near each other based on attractions and repulsions, like little force fields, and that actually none of this is anything. And at that point, I stopped thinking about it. It's all just energy. Okay, we're going to need to define a few terms, energy and systems. Do I still have it for this? Nope. We have systems, environment, and surroundings. So anything under observation is a system. Anything that is not part of the system is the surroundings. And we'll talk about closed and open systems. So, what is the system in the picture to the right, and what is the surroundings? Let's say we did a Science 10 lab, we're going to measure potential kinetic energy by throwing everybody off on bungee cords. Yes?
The system would be the individual jumping, and then surrounded will be everything else, like the forest.
Well, there's nothing other than the person,
The bungee cord?
Well,
Pardon?
The bungee cord?
the bungee cord.
Furniture?
So yeah, that you can see there's a platform. All of that would have to be, that would be part of the system you're observing. And then the parts that ideally shouldn't interfere with this would be the surroundings. So what are the surroundings? Trees. Trees, water, pardon? Cliff, rocks.
The cars.
What?
The cars.
The cars? Oh, there are cars. Air. What about airs would make you worry about this?
I don't know, it's just air.
Outside.
Wait, what do you mean? Like, what if you get
You're
struck-
jumping off.
struck by lightning?
Lightning. So weather.
Wind.
So we've got wind. We've got lightning. Jumping off of this, off of a metal platform in the middle of a lightning storm would probably be a bad idea. I knew someone who, it wasn't bungee cording, but they, there was a swing set up in Vancouver. It was at a very cliff edge like this, and when you went out on the swing, you were over the tops of the trees. And then you'd swing back. Great fun. It was old. When he was there, I wasn't there with him this time. He was by himself. And he swung over, and then the rope snapped. He fell straight down. At the bottom, there were some old logs that had been, they were in a triangle shape. So one log fell, another log fell like that, and then another log had fallen like that. He went through all three of them and missed all of them. If he had hit either one of them, he probably would have died like that. Hit soft mud and only broke, I think, 5 of the vertebrae in his back. Someone eventually heard him crying for help. He was in the trees, but this was a cliff edge, and then he was down there, and then there was beach. So people were walking along the beach. He yelled. Eventually they heard. They called 911. They couldn't get him from up on the road, so they actually had a hovercraft search and rescue come in, bandage him up, take him in. He can walk. He wore a cool cast that was like armor until his spine. Nothing, his spine never severed. He was incredibly lucky. So he was intending for the system, but then all of a sudden the surroundings became part of it.
Yeah, like how much would that lawsuit be?
What lawsuit?
Like from the things now. Can you not sue for that?
Why would you sue?
And
Who would you sue?
The company.
What company?
The swing company.
He found a swing in the forest
Oh.
and decided to swing on it.
Oh, if it was like
It wasn't a bungee cord, I said. It was just a regular, someone just made a rope swing. I've been on it a few times. It was like, we knew where the swing was. It was fun.
Sue everyone.
Yeah. But, yeah, if you found something like that. But, yeah. Yeah. So, when we consider the universe is your system plus your surroundings. When you run an experiment, you'll sometimes spend a lot of work making sure that the surroundings aren't affecting your system. When you do chemistry, you have a beaker that isolates all the chemicals from the surroundings. As long as it doesn't react with air or anything like that, you're pretty good. I know someone who was getting their PhD. They spent most of their PhD just building a box. It was a box inside of another box, which is inside of another box, which is inside of another box. And they spent years building the box. When they were finally done building the box, they just ran their experiment. It took like 10 minutes to collect the data, and then they were done. And they wrote their paper. Because the box within a box within a box within a box dampened all vibration. So if there was a truck going by the university a mile away, that would affect his experiment. If there was someone walking in the hallway, that would affect his experiment. So his experiment required him to make sure there was absolutely no vibration from everything. And that was a brand new experiment that nobody had ever done before, and by doing that, he was awarded his PhD after he defended it. Energy creates change in the system. Energy cannot be created nor destroyed. You cannot get order out of disorder. Earth has these weird things crawling all over the surface. burping, farting, building buildings. Where does all that energy come from to make all of that order? Yep.
Plants, animals,
Yes, where do the plants and animals come from?
Surrounding
other plants and animals, and the sun.
The sun. Ultimately, we used to think it was all the sun, and it's still 99.9% all the sun. The sun creates the plants, and it doesn't matter if you're an obligate carnivore. Ultimately, your energy comes from plants, because whatever you eat eventually ate plants.
Wait, so burping and farting come from the sun?
pretty much.
Ultimately, it's a sign of your metabolism, and your metabolism is from the food you ate, which is ultimately from the sun.
Wow.
Now, there are some, now we have learned of some other systems on our planet. There are some creatures that have grown next to volcanic vents in the ocean where there is no sunlight, and they process the chemicals that come out and use that for energy. So we have found areas that use things for energy that aren't the sun. They're rare because the sun is so much more plentiful, but they do exist, which creates some hope and questions for if you're looking for life on other planets, it could be underneath an ocean crust.
Did we get it from like stars?
With not enough sunlight from stars, but theoretically it does provide some energy. Yeah, but the amount, it's a bit like gravity. You go one distance, say that amount of sunlight, you go the same distance again, it's divide by 4, then divide by 16, then by, so it goes out so rapidly that you don't see
By
it.
every star around.
Yeah. Oh, Newton proved, way before we could actually tell, on that basis, how do we know the universe is not infinite?
Because we see way more stars.
Pardon?
We see way more stars in the sun.
Way more. And if it was infinite, even if they were very far away, you would have an infinite amount of light coming in, and we'd be fried. So there has to be a limit to the amount of stars, because we do not have that much light coming. Because light goes somewhere, and eventually there would be enough hitting us, unless it was created large very quickly or something. So he proposed that as a proof, and it stood until this day. Yes, Ariel.
Well, then how big is the universe?
Oh, we have measured how big it is. I don't actually know, but it seems like a useful question, given that we're doing physics.
Isn't it like something gazillion?
Yeah, it's fairly big, and it's expanding faster than light moves. So it's expanding faster than we'll ever be able to explore.
Right, 'cause it's expanding at light speed going...
Faster than light speed.
Wait, how does it expand faster than light speed?
It is.
I thought nothing could go faster than light.
No.
Because it's going light speed in two directions at the same time? Is that
The whole thing's getting bigger. How can it expand faster than light speed? What limits things from going light speed? Mass. The universe expanding is the shape of the universe. It's not mass. So it can expand faster than light. It's approximately 95 billion light years in diameter.
Pretty big.
So it's pretty big.
Is there like a visual?
I'm looking. I thought there was on this particular page, but now there's usually that slider one, and I'm not seeing it. If we have time, we'll do some more space science, but it will depend. Yeah.
You said diameter, but how do we know the universe has like that? Because diameter is for circle. So do we know?
Yeah.
How do we know it's like a circle?
like 1 year?
Yes.
Spherical.
1 light year.
Yeah.
In our observations, in any direction, it appears to be spherical.
Yeah,
It also appears to have wider than it is tall, so it actually has there's a plane if you wanted to orient yourself into it. Yeah,
It could be like a square.
it could be. It could be.
That's gonna be
Weirder
our
things have
universe.
happened.
Wait, isn't it
Why the universe is a
like,
square?
don't we know 100% that it has to because if it's expanding at light speed this way, expanding at light speed this way, the
Yeah.
total is expanding twice that way.
Yeah,
And
it's
doing that
expanding in all directions,
in all directions at
Yeah.
light speed.
faster than light speed.
What is it expanded into though?
But
This question doesn't make sense. There's nothing for it to expand into. There is no it for it to expand into. It is just getting bigger. It is not expanding into anything. It is.
Space to get bigger.
This is hurt
Pardon?
my brain.
You need something.
No, space itself is getting bigger. So I'm not saying the universe is getting bigger within something. I'm saying the concept of space itself is what's getting bigger.
I see.
So, and it's not just the universe. Like, yes, the actual fabric of space you can be in is getting bigger, but the actual size of atoms are growing as well as part of that process. Not as fast as the size of the universe. Eventually, we will be at a point when you look at you would try to look at a galaxy from within our galaxy, and you won't see them. They'll be too far away. That's quite a ways in the future. But yeah, everything's going apart from each other in all directions. And it's space itself. It's like saying what was there before the Big Bang. There was nothing before the Big Bang. The Big Bang was the invention of time. So there cannot be a before. Yes.
Isn't there like a thing they call like the great attractor or something, and like it's for like everything towards it? Something like that, right?
I think the great attractor, I may be completely wrong. I believe that's the term they gave to some large masses before they fully knew what black holes were. So there do seem to be some mass, like everything rotates around the center of a galaxy. They now think there are large black holes in the center of the galaxy. That's part of what holds everything together.
Oh, I see.
Yeah. There might even be little mini black holes in like the center of our sun and stuff. Yeah. But they're small, so they don't absorb very much very quickly. So they don't, a black hole takes forever to get very big. Okay. There it is. Sorry, thank you. Energy can be what or what from the system?
created or destroyed.
No.
Oh, transform. Converted.
We're going for the
Transformer.
transferred would work. It doesn't use two words, but I can just get rid of it then. It can be transferred from system
Isn't that really
to or from surroundings.
That's right.
I was just going to use, energy can be added or taken from the system to the surroundings, whichever one you want. In this particular one, how do we add energy to that system?
Give them a good push on the way down.
Pardon?
Like the elastic energy?
No, how do we, if we have this system right now, how would you add energy to that system?
Give them a good push on the way down.
A good push on the way down,
Put a weight on his back.
weight on his back,
Put a rock in
Take them to a different planet where there can be more gravity.
Lie.
add weight, a push.
Make him do a backflip.
Well,
Planet.
no, that's a good one. Would him doing a backflip change the energy in the system?
Yeah, he's like accelerating.
Not really.
Well, he's moving, but if he does a backflip, has any energy changed? No, his mass hasn't changed, his velocity hasn't changed, he's moving, he's using up some energy and transforming it within the system, but you haven't added any energy to the system.
But like, you could
Oh,
change
please
the
do not just start talking, I need hands. How can we add energy to the system that didn't involve a person doing something? How would the surroundings add some energy there?
Add like rockets to surround.
No. In that system as it is. So doesn't need a person, you're not gonna go buy rockets and add it. That system, how would the surroundings pass on energy?
It could rain and then make him like more heavier because of water.
Yeah. Rain. Adds mass. And someone said push, you don't need a person to push, you can have it pushed by wind. Yes.
A different planet with more gravity.
Again, you've now changed the entire surroundings. I said those surroundings.
Or if it started raining rockets.
How could we remove energy from the system and into the surroundings? Yep.
I don't know.
Yep.
Take away weight, would that be a limb or a head or whatever?
I'm anti-Rush.
Limb is lost. Maybe he hits a tree. So if you lose mass, you're definitely going to do it. That's I've heard. If you want to lose 10 pounds like that, just cut off a leg.
Oh, please.
Put him a parachute.
Oh, that is. He has the parachute.
Yeah. You open.
And what is the parachute doing?
Stop it. Well, not
How,
stop
yeah,
it.
but what is it using of the surroundings?
Air.
Air. So we got air resistance. And you have air resistance either way, but if you use a parachute,
What if you have like a rocket, but it lost?
no, we're not going to add rockets to it already. Just that system as we have it.
What if we just remove the system entirely? And it's just
But we're examining the system. That's part of what we're
what if you
doing.
remove like
No, that's not the question.
rope and
Nope.
He
Nope.
got chosen over
Nope. Go.
Shortening the cable, so that way you have less time to fall, less distance to fall.
Oh, again, now you're changing the system. I want to know what could the surroundings do that would take away your energy?
The river rises,
Yeah?
like a lot, so then that way you have less distance to fall.
River rises. If you start to, there are some where they've calculated the weight and the elasticity that when you go over, it's just enough to dunk your head in the river. And so when you do that, you would change your mass because you pull some water back with you. There'd be some resistance and friction when you hit the water. And certainly if there's some sort of accident where the river rises or, God forbid, rocks roll down, and if you change that part of the surroundings, you might change what you interact with. Yeah. Okay, good. Zoe, Ariel, I think one desk apart each would be good.
No, but we're talking about we're talking about specific.
One desk. One desk
Well, you
apart.
can ask for.
No, but we're not doing spaghettification into black holes.
But like.
One desk,
within,
one desk apart. Useful and not useful energy.
Yeah, limbs, well,
These are the rules of thermodynamics. I like to summarize them as you can't win, you can't break even, and you can't even get out of the game. That's the third law of thermodynamics. Because you could get out of the game if you could reach some state like hitting absolute zero, but you can't hit absolute zero, so you can't remove yourself from this process. You can't win is a rephrasing of what we just said. The first law of thermodynamics, energy cannot be created or destroyed. So you can't win. You can't end up than more than what you have. Yes?
so like before the Big Bang, there was nothing.
Yeah.
Big Bang happened, now there's energy.
Yes.
So energy got created.
We're not entirely sure because if I put it in another way, this process happens all the time. A particle a gentleman won a Nobel Prize for doing this, and what he did is he took two thin plates and discovered that this has actually occurred. So if you take absolutely vacuum, you sucked all the air out, or you put yourself in the middle of space, there's not a particle inside this box. You can measure a force. There are particles that are being created, and one is regular matter, and the other particle will be antimatter. So they are the same particle, but they're matter-antimatter twin. And that happens all the time. This is roiling all the time. And then immediately, they react with each other because they're matter and antimatter, and they annihilate each other. And what does +1 and -1 make? Zero. So you didn't have energy to begin with. You had something, but then it went away. Doesn't break any laws. It does that. It's like it was created, except it was balanced.
But isn't the whole
I'm going to finish. So What a gentleman did is he took very thin plates, put it in a vacuum, and he was able to measure the force across those plates because he was able to prove that if this is actually happening, then there could be situations when a particle is on this side and a particle is on that side, and because there's a plate in between, they fly away. The reason you can actually see black holes under some circumstances is because those particles, if you have the event horizon, will appear on both sides, and one will get sucked in and one will be just to the point it can escape, and that will lead to a form of radiation. So when they talk about how did our universe begin, they're talking about some sort of process like this. What we don't understand is that it turned out to be slightly asymmetrical. The universe absolutely created antimatter and matter, and they annihilated each other. But for some reason, where's the antimatter now? And why do we still have regular matter left? So there was some asymmetry, and what process created either that asymmetry or not all of it reacted. Maybe there's planets out there made of antimatter. We think we'd be able to detect that, and we haven't detected it yet. But it's like, yeah, where did it go? But the process they talk about is a process by which it's not so much that it was created, it's that it was balanced. Go.
Okay, but then can't, like with thermodynamics, you can't have negative energy. Isn't that the whole reason?
If you know, you could theoretically have it, and if you have negative energy, we'd be able to do some really cool things like anti-gravity machines. We don't think we can make it,
So, but then.
but yeah.
But like the whole thing is that you can't get out because like there is nothing below zero. But if there is
But
below zero.
remember, energy's not a thing, it's a property.
Yeah.
So if you have stuff, and as long as it's created in a way that, because matter cannot be created nor destroyed either, it's a property of matter, when we measure potential energy, kinetic energy, it's not that the stuff is there now. That stuff has energy. But when you have that stuff, you can't make any more than what you have. Now, if you could figure out a way to make these universes inside of a little machine and start running an engine on it, that would be pretty cool. Maybe you could. But so far, this is one of those rules that every time someone has said that they have managed to make a perpetual motion machine, it has always been wrong. We've never found a way to do it.
Isn't absolute zero just like theoretical?
Yeah, we can't get to it. We can get really close.
Do they know? Do scientists know of anything that is it? Or
If you turn helium into a solid, you're about as close as we can get.
What is that?
Which-
And you get way more like helium, like on the periodic
It's
table,
like-
the noble gas.
it's like
H.E.
when just
Yeah.
it's so cool that like the molecules.
Yeah,
Just stop.
and absolute zero is like even the electrons aren't moving, and that will never happen. However, you can get it really close, and when that happens, you can actually get some weird other states of matter that are beyond liquid, solid, plasma, gas.
States of water with that.
Sorry?
Isn't there 11 states of water you get?
Yeah, there's the other, but that refers to its crystallization. It's not, they're not that weird. Yep.
We have been able to solidify helium.
Yeah, that used to be the definition of an absolute zero for a long time, because that's as close as we could get. Now we can calculate theoretically, and we kind of know what it would be. Your head was up, no. Now, you can't break even is saying if you can't make energy, can you at least, if you put 100 joules in, get 100 joules out? And the answer is no. Oh no, I'm going to phrase that differently. When energy is transformed, some is always lost. And I'm going to highlight the word always. And it's usually is heat. So one of the reasons I've heard, particularly my relatives, say things like, solar is silly and electrical is silly. We're burning coal power plants to power our electrical grid for electric cars. Why not just put gas in the cars? The efficiency of a car is like 30 to 40%, and that's for a really efficient car. Cars are not efficient energy users. A lot of that's wasted as heat and noise and all sorts of things. An electrical car can get up to 80% efficiency. And we're not even at a good point in electric cars. We're still starting out on that. We probably can get more efficient. If you make use fossil fuels to make electricity that you then transport into a car, you actually get more of the energy out of it and less is wasted. And so it ends up actually decreasing the amount of fossil fuels and CO2 in the atmosphere. It would be better if we didn't burn it to begin with. We found other ways, nuclear, solar, whatever. But you can't break even. We're not going to get 100 joules out of 100 joules. If we're really lucky, we'll get 99, but we're probably going to get somewhere between 20 to 80. So some energy is always lost. All energy transformations result. Oh, I wrote that up there. It's the same thing. As some loss, usually heat.
But when you transform, say, like physical energy to heat,
Mhm.
can't you get that to like a
Heat,
percent?
heat is always considered a loss because eventually that just dissipates into the environment. You can't capture it very well. If you can get a heat difference, you can recapture that back as electricity, but the efficiencies always are fairly low.
Okay.
So we like those
So
when we have like a
excluding a heater.
yeah. Heaters is one of the most efficient things we can do because all the waste heat, all waste energy comes out as heat. But there's light there. Like it glows. You don't want sound. You don't want. There's some of it that will be lost in a useless form. But heaters can be one of the most efficient things because they are producing heat. But the heat itself is going to heat the room and then go out into the water heater. It's if you want to transform like temperature differences into energy, it's useful to have something big like a planet because it's relatively inefficient. But if you can dig down and get somewhere that's always one temperature, then you're up top, and then you can start doing some fancy things.
Or geothermal.
Geothermal. Yeah. The system below on your page is designed to transform electrical energy into what? What is that?
Light.
And heat.
Yeah. And the fancy word, now that's light energy. The fancy word for light energy is radiant. Hold it, is radiant spelled with an E there? Yeah, I think it is. Double check my notes. I think I should have it. Radiant energy. Now it looks wrong again. I'm going to ignore it. Now in this system, where are we going to lose our energy? It's not all going into light. There's an old incandescent bulb. Yeah,
As some heat.
has some heat. And the fancy, what's the fancy word for heat? Thermal. If there's any motion at all, absolutely. Light bulbs don't tend to move very much.
The filament inside, it expands and contracts.
Pardon?
The filament inside, it expands and contracts.
Oh yeah, and that'll eventually break it too. Yeah. Radiant energy. Useful. I'm going to add more arrows for that. And then you have thermal. One of the great advances with LED lights and other such things was not that they're particularly efficient. They're still not. But it's just that so much less of their energy went into thermal. But they're not cold. They're still a big chunk that goes into thermal. One of the big problems with still doing like stage lights out of LEDs, so you pack all the LEDs in one spot, and they're all made out of plastic, so they melt. Whereas something made out of glass and steel can get really quite high temperature and doesn't melt. So being able to get them bright enough without melting is still a problem. Thermal, not useful unless you have one of those old Easy Bake ovens. Did anybody grow up with an Easy Bake oven? Did you cook anything in it?
I still have it.
And what did it use as its heat source?
Like the lamp.
Just, yeah, it was just a little light bulb. They've discontinued making it, sadly. It's one of the best expressions of chemistry as a chemistry kid I've ever seen. It's beautiful. And we also have, I'll say expansion, because vibration often just means really quickly, and I don't want to give the people the impression behind it. But expansion, like it's literally changing in size, and then cooling would change inside, and that takes energy to do of components. And Not, that is also not useful.
But more towards like the vibration, like this electricity going, you know, this constant, it's like very quickly going this way.
Oh, yeah, it's going back and forth.
Which causes it to, like, it's going through and then it stops. And as it does that, it would quickly just,
Yeah, that is what often heats up the wires too.
yeah,
Yeah.
that is.
And there are animals like every animal has a rate in which you can see that if the light is flashing fast enough, you see it as one continuous source. And for humans, I think, what do the lights flash at?
These ones usually go 120.
Yeah.
Usually 60 hertz is usually
And we don't see this as continuous lights. There are lots of animals. I think, I have to double check, I think cats are one of them, that see our lights as strobe lights. Because their perception is faster than ours. And we don't realize that when we make our lights, we are making things very confusing for some animals.
What's strobe light?
Oh, you've never seen a strobe light? A light that flashes on and off and makes everything go. Ah, totally needs to get a
So
strobe
is
light.
it broken
We,
light?
we should have a strobe light party.
So a broken light?
No, you buy it on purpose, and you put it in your dorm room in university, and then you have it flash, and then when you dance, it looks like people are going, and then like moving around in a jerky kind of, no one's ever seen, no.
And I know.
You've seen
yeah,
that
I know.
before?
I've seen it in a haunted house.
Haunted houses will use them too, because they're kind of cool.
I
Yeah.
saw it in a movie once.
Saw it in a movie once?
No, yeah.
So they see that like
Pardon?
they see that like
Yeah, they would see it very rapidly.
that's like continuous.
Now we are at 5 minutes too. I was hoping to stop. I won't do the rest. What I'd like you to do, pull out the next worksheet that we're working on, spend 5 minutes orienting yourself and do at least one question right now. So then everybody started. The second worksheet.
That's like they see that.
If you didn't get it, come up and get it. It looks like this. I know one person has done it. Not easy.
So they don't know. They don't know. They don't know. They're so cool.
I don't think cuts are. I'm gonna finish it
Wait,
first.
say he
They're
has
really
one.
heavy.
Wait, say he
They're
has
heavy.
one.
They see bigger. Yeah, they're heavy.
Oh, for that. Ah.
Thank you so much, Zane. Oh my. Zoe, can you look at
Oh, yeah.
really good at
Wait, no.
Yeah.
It's not. Do cats have 7 or 9 lives?
In traditional culture, they would be said to have 9 lives.
Oh yeah.
Although it's interesting, 7 is a lucky number and is also regularly
Yes,
used.
I hear my grandma say
The
seven.
cat.
Yeah, I wonder
You don't
if
know.
that changes depending on where you're from.